There are many mysterious and fascinating natural phenomena around us. And a rainbow is one of them. How does a rainbow form? In order for a rainbow to form, it needs sunlight. In addition to visible light, the sun emits X-rays, ultraviolet rays, and infrared rays. These are all called electromagnetic waves, and they differ only in wavelength. The light we can see is part of electromagnetic waves, but it is specifically called visible light, because the human eye is sensitive to it. The wavelength of visible light is about 400 to 700 nanometers, and we see violet, blue, green, yellow, orange and red. Yes, just like a rainbow. In fact, there is a relationship between the order of rainbows and their wavelengths. Most rainbows can be seen after it rains. After it rains, there are still many water drops in the air. In addition to the sun's rays, these water drops are necessary for the rainbow to form. As light enters water from air, refraction occurs at the boundary of materials. When refraction occurs, the direction in which light travels changes. The relationship between the angle of incidence, theta, and the angle of refraction, phi, can be expressed as in this equation. N is called the refractive index, and it varies depending on the material. In addition, the refractive index must change depending on the wavelength in order for colors to be separated like a rainbow. This phenomenon is called dispersion of light. Now, let's try an experiment to see for ourselves. In this experiment, we will examine what happens when light from a lamp passes through a prism. Let's use the minimum deflection method to find out if dispersion is occurring, and how much the refractive index really changes with wavelength or frequency. First, let me explain the principle of the measurement. When a monochromatic light beam enters a prism, it looks like this. The angle, delta between the incident ray and the transmitted ray is called the deflection angle, and it depends only on the incident angle, I. When the incident angle, I, is changed, the deflection angle, delta is minimized at a certain incident angle. It's called the minimum angle of deflection, delta 0. The relationship between the refractive index, n, and the minimum deflection angle, delta 0, is shown in equation 1. And the refractive index, n, can be obtained by finding the apex angle of the prism, alpha, and the minimum deflection angle, delta 0. This is called the minimum deflection method. Next, I will explain the experimental procedure. The first thing we have to do is to adjust the spectrometer. After that, we measure the apex angle of the prism, alpha. Next, we measure the minimum deflection angle, delta 0. And finally, we calculate the refractive index from these measurements. First, let us explain the adjustment of the spectrometer. Turn the eyepiece, indicated by the arrow, so that the cross wire is clearly visible. Next, look through the telescope at the distant view, and turn the focus adjustment handle, indicated by the arrow, so that the distant object is clearly visible. Level the surface of the prism stand. Place the arm of the leveling tool above the adjustment screw of the prism stand, and turn the screw to raise the height of the prism stand until it touches the arm of the leveling tool. Use the 3 adjustment screws to adjust the height of the prism stand. Place the mirror on the prism stand as indicated by the arrow, and look into the mirror with the telescope. At this time, place the prism stand so that one of the screws is in front of you to make the next adjustment easier. Turn on the LED light. Remove the cap, indicated by the arrow, and insert 2 batteries. When you want to turn on the LED light, turn the part indicated by the arrow to the left, and to turn off the LED light, turn it to the right. When not in use, turn off the LED light. Turn the prism stand to bring the reflected image of the autocollimation prism into the field of view. Turn the focus adjustment handle so that the reflected image of the cross wire can be clearly seen in the reflected image of the autocollimation prism. When the telescope is in focus, both the real and reflected images of the cross wires are clearly visible. The next step is to adjust the collimator. Remove the mirror and make the slit of the collimator horizontal. The width of the slit should be about 1 to 2 mm. Next, turn on the cadmium lamp. The pink label indicates the cadmium lamp and the gray label indicates the sodium lamp. Plug the lamp into the socket of the lighting device. There are two types of lamp legs, thick and thin, so make sure they are oriented correctly. Next, turn on the power switch and press and hold the start button. After waiting for a few seconds, when the filament of the lamp turns red, remove your finger from the start button and the lamp will light up. The color of the light is white at the beginning, and turns to blue color after a little while. Take measurements after the lamp turns blue as shown on the screen. Wait for a few minutes after the lamp turns on to confirm that it is stable, and then cover it to block light except in the required direction. At this time, the lamp is very hot, so do not touch it. Also, do not leave the filament red for too long time. To turn off the lamp, turn off the power switch. Place the cadmium lamp in front of the collimator and look through the collimator with the telescope. Place the light source as close as possible to the collimator to allow more light to enter. Make sure that the horizontal image of the slit is in the field of view. Turn the collimator's focus adjustment handle so that the image of the slit is clearly visible. Once the slit is in focus, you can see the scratches and dusts on the slit. Never touch the telescope's focus adjustment handle after this. The next step is to align the prism with the optical axis. The prism should be held at edges. Do not touch the sides of the prism to avoid contaminating the surface through which the light passes. Also, be careful not to break the prism by dropping it. It is easier to adjust the prism, if it is placed so that its position in relation to the adjustment screw on the prism stand is as shown on the screen. The frosted glass surface of the prism is the BC surface. Place the prism so that the AB plane is orthogonal to the line between S2 and S3. Next, make sure that the image of the slit reflected by the AB face of the prism is visible in the telescope. Adjust the tilt of the prism stand so that the image is at the center of the cross wire. Turn the S2 or S3 screws so that the horizontal image is at the center of the cross wire. Then, adjust the AC plane in the same way. In this case, do not touch S2 and S3, but tune S1. Repeat this procedure for both the AB and AC planes so that the horizontal image of the slit is at the center of the cross wire. Now it is time to measure the apex angle, alpha. Set the slit to vertical. Place the image reflected from the AC plane of the prism into the field of view of the telescope. Align the vertical image of the slit with the center of the cross wire using the fine adjustment screw. When you have brought the image to the center of the cross wire, press the reset button on the counter to set the value to 0. Next, align the reflected image of the slit with the center of the cross wire in the same way for the AB plane. The value of the counter at this point is the angle, theta. The apex angle, alpha, is a half of theta. Measure the apex angle several times by turning the prism stand or changing the position of the prism. Average the values to get the alpha value. The next step is to measure the minimum deflection angle. Place the prism so that the light passes through the AB and AC planes roughly symmetrically. First, make sure that you can see the image of the slits, or spectral lines, separated into different colors. In the case of the cadmium lamp, the 5 colors described in the text are visible. Slowly rotate the prism stand in one direction, and the spectral lines will move in the field of view. There is a position where the direction of movement of the spectral lines is reversed. The angle at this point is the minimum deflection angle. Fix the prism stand at this position and align the cross wire to the spectral line. Then reset the counter. Turn the prism stand and the telescope, and do the same on the other side of the telescope, and read the value of the counter. This is the angle, beta. Half of this is the minimum deflection angle, delta 0. Measure the minimum deflection angle for each spectral line. This completes the measurement of cadmium lamps. Here is how to organize the measurement results. Substitute the measurement results into equation 1 to calculate the refractive index for each spectral line. After that, make a graph of the dispersion relation, with the frequency on the horizontal axis and the refractive index on the vertical axis. The graph of the dispersion relation should look like this. Next, let's consider this problem. If we assume the prism as a group of oscillators, and the oscillators are forced to vibrate by the interaction with light, the relationship between the refractive index and the frequency is as shown in equation 2. The previous graph is in accordance with this equation. In order to make an accurate comparison, equation 2 can be converted to a linear equation using this relationship. If we consider the measured data in this linear equation and plot it on the xy plane, the data will align along a single straight line. Find the slope, a, and the intercept, b, by the least square method, and then find nu p, and nu 0, from the equations. Next, let's find the frequency of an unknown spectral line from its refractive index. Measure the refractive index of the D lines of the sodium lamp, and find the frequency using nu p, and nu 0 that you found earlier. In the case of the sodium lamp, only 2 lines of the orange-colored spectrum are visible. These are the D lines of the sodium lamp. This is the end of the experiment. In your report, please summarize the following. For more details, please read the textbook. That's it for the explanation. Now let's start the experiment.